Welcome to ePathshala lecture series on computer science. In this module on data analytics, we will be discussing about sampling distribution and statistical inferences related with analytics. In this module, we will be learning the basics of sampling distribution, followed by the fundamentals behind statistical inferencing and reasoning, and finally, we will be understanding the basics of hypothesis testing, which might be applicable for analytics. So, to start with, we will first understand sampling distribution. So, what exactly is sampling distribution is? It is fundamentally a distribution created by means of the sampling procedure. So, what exactly we are trying to do is, we are trying to make use of or employ the rules of probability and the laws of expected value and variance to derive the sampling distribution or the sample distribution. So, when we choose say the samples from the original population, how these samples are distributed, and this distribution will help an analyst to visualize to what extent the sample that has been collected reflect the original data set's property or say the properties exhibited by the original data set. So, sampling distribution, fundamentally we need to collect large samples, only then the distributions actually tend to be say normal. So, we need to make the distribution normal to the maximum extent. So, when we can end up with say an approximate normal distribution is only when we collect a large amount of sample. So, when we are sampling, we need to see what is the maximum extent of data that we can collect and hence make the distribution normal. So, the sampling distribution is centered on m. M is nothing but the mean of the population. The standard deviation of the sampling distribution can be computed based on the standard deviation of the population divided by the square root of the sample size. So, we can compute the mean and the standard deviation, with which we can come to say certain parameters which will talk about the sampled population. So, we need to make use of a theorem called central limit theorem. So, the sampling distribution of the mean of a random variable, say for example x, which is related to the sample data that is drawn from any population, is going to be approximately normal for a sufficiently large sample size. So, what does this central limit theorem states is, it states that when we want to have a normal distribution, we need to have large number of samples. So, this is what I mentioned in the first slide. So, the larger the sample size, the more closely the sampling distribution of mean will resemble a normal distribution. So, when we go in for larger number of samples, naturally the mean of the sample will represent a normal distribution. Now, let us understand how this sampling distribution and how sampling distribution will tend to become normal when we go in for large number of samples with an example. So, assume a fair die which is thrown infinitely many times with random variable x, which indicates the number of spots on any throw. So, what is that we are trying to do is, we are trying to compute the probability of say the spot for each and every throw. So, now let x indicates the number of spots that is exhibited as a result of any throw. So, when you take a die, you can find one spot or at the maximum of 6 spots on one side of a die. So, we need to compute the probability of these spots with respect to every throw. So, if x is the number of spot on any throw, then probability of x is going to be equal to 1 by x, which is nothing but 6 here. The reason, we are going to have say 6 number of spots. So, it is going to be 1 by 6. Similarly, the probability of say 2 number of spots associated to any throw will be equal to 1 by 6. Similarly, for all these number of spots, the probability is going to be the same. So, now when you take a look at this, the distribution of this probability value is going to be same. From this probability value, we can compute the mean and variance. So, using the formula summation of x multiplied by probability of x, we get mu. So, which is nothing but the mean. So, mu will be x, say the number of spots on the particular face associated to a particular throw, which is 1 multiplied by probability of that particular spot. So, which is going to be 1 by 6, and since this is a summation for each and every number of spot on any throw, we need to make use of this product, that is the number of spot which is the x value and the probability of that x value. So, it will be equal to 3.5. Now, we need to compute the standard deviation, which is indicated by sigma square. So, sigma square will be equal to summation of x minus mu, which is nothing but the mean, and the whole square of this multiplied by probability of x. So, now this value will be 2.92. So, sigma will be equal to square root of sigma square, which is 1.71. So, now for a single die with say some number of spots on any throw, we compute the mean and then sigma. Now, what does this mean and sigma indicates is, it is nothing but a measure of central tendency. So, to what extent the population is associated to say a central value. So, the central value which is exhibited or which is associated to this example is 3.5. Now, consider another scenario where instead of using one die, we will be using 2 dice. Now, what is that we are going to do is, we are going to compute the sampling distribution by taking a look at all the samples of size n is equal to 2, where this 2 indicates the 2 dice and their means are shown in this particular chart. So, the sample 1, 1 indicates in one die the number of spot is 1, and in the second die also the number of spot is 1, and the mean of this particular sample is 1. Similarly, for various samples, the corresponding means are highlighted in this chart. Now, when you take a look at this chart, you may find there are totally 36 samples associated with this given scenario. Now, what is that we need to do is, we need to now make use of some other parameter which may be used for representing these 36 samples. So, when you take a look at the mean, you find few values of these mean being repeated in this chart. So, instead of we depending on all these 36 samples, now we can represent these 36 samples by their mean. So, what is that we are going to do is, we are going to make use of the mean. So, there are only 11 values for the mean. So, instead of 36, now we are going to work on just 11 values. These 11 values are nothing but the mean related with the samples, and out of these 11 mean value, you may find few mean value. For example, the mean value of 3.5 occurs more number of time when compared with some other mean which may be equal to 1. So, in this chart you find few of the mean value occurring many number of time when compared with the other means. Now, what is it we need to do is, we need to compute the mean and standard deviation for the sample which is represented by means of its mean. So, with respect to the mean, we are now trying to compute the probability of the mean. So, here the mean value will be our sample and we are computing the probability of these samples. So, based on these values, we compute the mean of this sample mean equal to 3.5 and the standard deviation of this sample mean equal to 1.21. Now, when we plot the mean value and we find the distribution of the mean value as shown in this chart. Now, when you take a look at this chart, you find say the value 3.5 which is associated to the mean has occurred more number of time when compared with say the mean value 1, and all the values over here highlight the frequency of occurrence of the mean value with respect to the given sample. Now, this is the distribution which has been generated for the scenario wherein we used 2 dice, and this is a distribution associated to the scenario wherein we used 1 die. Now, when you take a look at these 2 charts, here you find the value 1 till 6 has been equally distributed, and here the values which are nothing but the mean Now, here instead of the real samples or the real population, we are going to make use of the mean of the population for representing the original population. So, here you find the distribution of a mean has been properly ordered, and you find this distribution is approximating towards a normal environment. So, when we take a look at this chart, we come to a conclusion that when we increase the number of samples, naturally the distribution of the sample tends to be approximated towards normal. So, this example will help us to understand the central limit theorem that will clearly states that increasing the number of sample will always make the distribution more normal. And also we can note that the population mean is equal to say the mean of the original sample, and the sample means standard deviation is equal to the standard deviation of the population divided by 2, which is half of the population standard deviation. So, to generalize, for a single die we found what was the mean, and for a 2 die the mean is going to be mu of the original sample, and the standard deviation is half of the population standard deviation. Now, for n dies we can generalize this. So, here instead of by 2 we can use n. So, a more generalized way by which we can represent the sample's standard deviation and mean will be equal to sigma square divided by n for the standard deviation, and mu of x bar will be equal to mu, which is nothing but the mean of the population. So, the standard deviation of the sampling distribution is actually called as standard error, and that is provided by sigma by square root of n. Now, when we are working with respect to various sampling techniques, what happens is sometimes bias in terms of the data that we have selected comes into picture. Therefore, sampling and the distribution of the samples need not be normal. So, in such scenarios we will have to go in for resampling. So, we will understand what exactly is resampling and how it eliminates the disadvantage of sampling. So, resampling methods actually frees the researcher from making certain assumptions which is related to conventional statistics. The assumption is whenever we collect samples, we assume it is going to be a bell shaped curve, and here the focus will be only on the statistical measure and their theoretical properties can be analyzed mathematically. So, what exactly happens is researcher need not assume the distribution of data is going to be a bell shaped curve, and hence they can make use of, or they can simply focus on statistical measures whose theoretical properties can be evaluated or analyzed mathematically. So, what is a resampling procedure is? Resampling procedure actually addresses a key problem in statistics, which is nothing but the data that we collect, if it is going to be incomplete, or if the data that we have collected for our sample is collected from an ill defined population, then resampling will come to an help, and therefore, we can make an analysis effective even from an ill defined population. So, this has been defined by Peterson in 1991 in the article published by him titled Pick a Sample in Science News. What are the various resampling methods? So, certain resampling methods that are closely associated with analytics are given here. So, few of the commonly used resampling techniques are highlighted here. So, the first technique is bootstrap method. So, in bootstrap method what we do is we draw the samples at random, and that is associated with the replacement technique strategy. So, what exactly happens is we choose the samples randomly and then we replace the sample that we have chosen once again back into the original population. So, this is a kind of sampling with replacement strategy, and this can be applied for the purpose of hypothesis testing, and also whenever we find some kind of bias towards the data set that we have collected can be easily validated using this bootstrap resampling method. The second resampling method is jackknife method. In jackknife method what we do is we will be leaving only one observation from the original population and the rest of the samples will be collected. So, the sample consists of full data set with one observation left out. So, this particular sampling procedure will be same as say the first method, bootstrap method, wherein it can be used for hypothesis testing as well as for looking in for biases. The third resampling method is permutation. In permutation technique, what we do is we sample at random and this is without replacement. So, therefore, the sample that we have chosen will not be replaced back into the original population, and hence the chance of selecting the same sample does not come into picture. So, this sampling procedure will be applied for hypothesis testing. And the last type of resampling methodology is cross validation. In cross validation, what we do is the data is divided into two or more subsets. Then what we do is we take from these subsets or we collect data from these subsets, and thereby we ensure that data is collected from each and every of this subpartition or subsets. So, this cross validation technique will be applicable for model validations. So, with these available resampling methods, we will be in a position to eliminate the bias which has been introduced because of wrong sampling techniques. Having understood what is sample, what is sampling and then resampling techniques, then we need to know about statistical inference. So, what exactly a statistical inference is? It is a process of reaching conclusions, and what is that we are trying to conclude is we are trying to come to a conclusion about the characteristics of the entire population using the subset of data which has been chosen as part of sampling. So, we are trying to reach a conclusion about the characteristic feature of the data or the original population with the help of the sample data. So, in statistical inference, what exactly we are trying to do is we are actually trying to guess the truth about the population. So, we are trying to look into the population parameter, and this is done from a sample statistic. So, assume this is the original population, the truth is not observable from the original population. So, what we do is we choose a sample. So, this is the observation made from the original population. For this sample observation, what we do is we compute the sample statistics. Now, with the help of these sample statistics, what we now try to do is we try to make a guess about the whole population. So, what we are trying to do is we are trying to follow a procedure, or we are trying to make use of a process with which we guess the truth about the population using the sample data which has been collected. So, the population parameters and the sample parameters are compared, and based on this comparison we understand whether the population exhibits say certain characteristic features or not. For this we need to make use of hypothesis testing. So, hypothesis testing is actually a procedure by which we infer two or more groups are different from each other. So, for this what is that we need to do is, as a first step we need to write the statistical hypothesis. Statistical hypotheses are described by mathematical terms. So, a statistical hypothesis always comes in pairs. One is a null hypothesis, another one is an alternate hypothesis. So, what is a null hypothesis? Null hypothesis is represented by the notation H naught. So, null hypothesis usually takes the following form: H naught implies say mu 1 is equal to mu 2, where 1 and 2 represents two different conditions. So, this is read as the null hypothesis is that the mean of condition 1 equals to the mean of condition 2. So, here when we take a look at this null hypothesis always deals with population parameters and not the sample statistics. The second thing is, null hypothesis must contain an equal sign of some sort, like equal to or greater than equal to or less than equal to. Now, when we take a look at this null hypothesis, statistical test which has been designed normally are designed to reject the H naught and never to accept this. So, this is one important point which every researcher must keep in their mind. So, any statistical test which has been designed will be only aimed towards rejecting the null hypothesis and not accepting it. So, once we know what is a null hypothesis, the next thing we should understand is the alternative hypothesis. So, alternative hypothesis usually takes the form H1 implies mu 1 not equal to mu 2. So, this is read as the alternative hypothesis states that mean of condition 1 does not equal to mean of condition 2. So, now when you take a look at this alternate hypothesis, this is also similar to null hypothesis. It is all about say the population parameter and not the sample statistics. Now, when we deal with respect to the null and alternate hypothesis, the null and alternate hypothesis must exhibit two important property. One is mutually exclusive, another one is exhaustive. Now, what do you mean by mutually exclusive is mutually exclusive means H1 and H0 cannot be true at the same point of time, that is either H1 must be true or H0 must be true. Exhaustive means the experiments that we conduct and the outcome of the experiments must make either H0 or H1 true. So, this is what you mean by exhaustive. So, null and alternate hypothesis must be mutually exclusive and exhaustive in nature. Now, there are directional and non-directional hypothesis. Now, whatever hypothesis that we discussed are non-directional hypothesis, because they do not specify how the mean should differ. That is, they do not say anything about the mean of condition 1, how it should be greater than or smaller than the mean of condition 2. They only state that the mean should differ. So, non-directional hypothesis are sometimes called as two-tailed test. So, a directional hypothesis always includes an ordinal relation between the means, that is they state one mean should be larger than or smaller than the other mean. So, for a directional hypothesis which is stated using the H0 and H1, it will be looking like this. So, for H0, that is for null hypothesis, mu 1, that is mean of one condition, will be less than equal to the mean of condition 2, or H1 will highlight mu 1, mean of condition 1 must be greater than mean of condition 2. So, the directional hypothesis are sometimes called as one tail test. Now, let us take an example where we try to convert word hypothesis into a statistical hypothesis. Now, assume we have a text document and then we find various words occurring in the text document. Now, what is that we are trying to do is we are trying to conclude that certain words occur frequently, and we also try to state that those words that occur frequently are easier to recall than the words that occur infrequently. So, what exactly we are trying to say is any word that occurs frequently in a document can be easily remembered, and any word that is not frequently occurring in that document or in the text is not easily remembered. So, how we can represent this using an hypothesis? So, for this first we need to know whether it is a directional hypothesis or a non-directional hypothesis. Of course, this is going to be a directional hypothesis. Now, first we need to write the relation which will be an alternate hypothesis. So, we are going to define H1. So, for H1 we say that the mean of the words that occur frequently is going to be greater than the mean of the words that are infrequent in nature. So, after writing this alternate hypothesis, now we can write the null hypothesis. So, anything that covers the possibilities that are actually not covered by this alternate hypothesis will be considered as null hypothesis. So, in other words, we write a hypothesis that covers all possibilities that are not covered by the alternate hypothesis. So, this is going to be the null hypothesis. So, the null hypothesis here is defined as the mean of the frequently occurring words is less than equal to the mean of the infrequent words. So, now we have taken a sample scenario where we are trying to state the feature exhibited by that text document using say a statistical methodology. So, we define an alternate hypothesis and null hypothesis, and then we try to conclude which one is true, and accordingly we bring out certain inferences about that particular text document. So, when we are trying to make conclusions, inferential reasoning is very essential. So, the statistical inference can never tell us if two means are equal, That is, it can only tell us if the two means are equal. Why this is happening is, statistical inferences never proves that two means are not equal. So, it tells us if the probability are not equal. So, it does not define that whether the two means are equal. So, if two sample means are different from each other, does that imply the null hypothesis is false? Practically speaking, no. And the reason behind this is, sample means are point estimates and they are not precise predictors of the population, and hence they change from sample to sample, and that is the reason even when two sample means are different, we cannot say that the null hypothesis is false. Now, when we are doing this inferential reasoning, we need to take a look at how these two population means or sample means need to be different, because when we want to conclude whether null hypothesis is true or when we want to reject, that is null hypothesis is false, then we need to check how to what extent the two sample means are going to be different. So, the answer actually depends on the distribution of sample means. So, when we take in more variables for our sampling distribution, then there will be more difference in terms of the sample means. Thereby, what we can do is, we can always state that the two sample means are completely different. So, now the answer is, it depends on to what extent we are willing to make an error and incorrectly reject when H naught is true. So, what we are trying to do is, we are trying to do or make an error, thereby we are trying to reject the null hypothesis. So, the less willing we are to make such an error, the larger the difference need to be. This type of error is called as type 1 error or also known as alpha error. So, alpha error is fundamentally an error that occurs when we reject H naught, in fact when H naught, that is the null hypothesis, is true. So, we are free to decide how likely we want to make or bring in this alpha error. So, the probability of making alpha error is given by a factor alpha, which is defined between the range 0.5 or 0.01. So, 0.05 and 0.01 says there is 5% or 1% significance with respect to this alpha error. So, whenever we state a null hypothesis and when we want to reject the null hypothesis, in fact when it is true, then we will be providing a significant range within which we can always reject it. So, that is what is stated by here by these values 0.05 and 0.01. So, this inferential reason, at some point of time we may not want to reject the null hypothesis, though it is false. So, in such scenario we will be looking in for alternate conditions. So, what we are trying to do is, when we want to make an alpha error, then we need to have alpha value and this alpha value will be chosen arbitrarily. So, before trying to make a conclusion, we should see to that to what extent the means associated to the two conditions are different. Now, when we want to make this H naught to be rejected, practically speaking this H naught may be true, but we are trying to reject it. But when we reject it, the only alternate thing that we can take is H1, that is the remaining hypothesis, which is nothing but the alternate hypothesis. Technically speaking, we are not accepting H1, that is once H naught is rejected, the only left out choice is H1. So, we never accept H naught as true either. So, we only fail to reject H naught. So, when we are rejecting, that is when we fail to reject H naught, we actually end up with say the population means and we conclude that the population means are different, but the sample means are not sufficiently different. So, we end up with the second type of error called as beta error or type 2 error. The second type of error actually can occur in statistical inference, which says that we fail to reject the null hypothesis provided H is already or really false. So, the two types of error we need to have a compromise. We cannot try to minimize both the errors and that is not at all possible. So, when we lower alpha level to minimize the probability of making type 1 error, the beta error will rise or the other way, when we lower the beta level or the beta error, the type 2 error, then the alpha level will rise. So, when we want to bring a compromise on these two type of errors, naturally we need to keep one thing low and the other thing naturally will be high. So, to summarize, in this module we discussed about sampling distribution and how knowledge about sampling distribution will help analysts to proceed in doing proper analysis. Hypothesis testing is one commonly used technique for statistical inferencing, and statistical inferencing and reasoning are very important for analytics for the purpose of working on, say, a subset of the original data and thereby making a conclusion on the whole. Thank you.